to begin our study of sequences, let's write the elements of a sequence. If I have a sequence a sub n, and the definition is 3 plus -1 to the n power, I can write the terms of the sequence like this. N is going to start with 1 and go up by integers. So a sub 1 would equal 3 plus -1 to the first, a sub 2, 3 plus -1 squared, and so on. Using this definition, I see that the first few terms of this sequence, when we have -1 to the first, this is -1 plus the 3 is 2. In this case, -1 squared will be +1, so this term will be 4. Then we go back to 2, then 4, and 2, and so forth. Let's look at another sequence. This sequence b sub n is going to equal n over 1 minus 2n. Again, we can replace n with the integers, so that b sub 1 is 1 over 1 minus 2 times 1, which is equal to -1. B sub 2 would be 2 over 1 minus 2 times 2, which would be -2/3. And then we go on to -3/5 for the next, and -4/7. Okay, another sequence, C of n is n squared over 2 to the n power minus 1. And for this sequence, we have 1, 4 over 3, 9 over 7, and 16 over 15. Okay, and these sequences that we've looked at so far have been written very much like we write a function, but there is another way that we can write a sequence, which is called a recursive rule. Let's look at one of those. If I have this sequence d sub n, I might write it this way. D sub 1 is equal to 25, and d sub n plus 1 is equal to d sub n minus 5. So what I'm saying here is that every time I want a new term, I have to subtract 5 from the term that I had before. In some ways, this is easier for many people to understand. The disadvantage of a recursive definition is that if I need the 10th term of this series, I have to find all terms up to that. So let's look at these. I've got d sub 1 equals 25. D sub 2 would be 25 minus 5, so 20. D sub 3, 15. D sub 4, 10. So this is a recursively written sequence. One of the things we want to do with sequences is to be able to find the limit of a sequence. To do that, we'll need a couple of definitions. Okay, so the definition of the limit of a sequence and you can see this on page 589 in your textbook. If I have L that is a real number, the limit of a sequence A sub n, which I would write limit as n goes to infinity of A sub n. If we call that L, then the following must be true. If for each epsilon greater than 0, there exists some m greater than 0 such that the absolute value of A sub n minus L is less than epsilon whenever n is greater than m. Okay, if this limit exists, we say that the sequence converges. If the limit does not exist, we say that this sequence diverges. Okay, also in your textbook, you've got theorem 9.1 that says if L is a real number and F is a function of a real variable, such that the limit as x goes to infinity of f of x equals L, and if the sequence A sub n is a sequence such that f of n is equal to A sub n for every positive integer n, then we can say the limit of A sub n is equal to L. So basically, if I have a function that has a limit and a sub n is a sequence so that the integer values, positive integer values of the function are equal to the elements of the sequence, then the limit of the sequence is also L. Let's work a problem where we find the limit of a sequence. So I've got a sequence, a sub n defined by 1 plus 1 over n to the nth power. Okay, back in chapter 5, you learned that the limit as x goes to infinity of this function 1 plus 1 over x to the x power was e. So we can apply theorem 9.1 and say that the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of 1 plus 1 over n to the n power, which is e. Okay, there are some different ways that a sequence can fail to have a limit. For instance, if the terms increase without bound, we could say that the limit as n goes to infinity of a sub n is infinity. Or if the terms decrease without bound, we could say the same thing, but it would go to negative infinity. On page 590 in your textbook, there's a theorem that describes the properties of the limits of sequences. I will not go through that right now. You can look at that on your own. What we will do now is determine whether a sequence converges or diverges. So our first sequence, a sub n, three plus negative 1 to the n power. And we determined before that the terms were 2, 4, 2, 4, 2, 4, and so on. Because these terms alternate between 2, 4, 2, 4, 2, 4, the limit does not exist. We're not headed toward a particular value. It just keeps oscillating. Let's look at another one. We looked at this one before as well. And to find the limit as n goes to infinity of this, going to divide this function by n so that I have the limit as n goes to infinity of 1 over n minus 2. And as n goes to infinity, this fraction becomes very, very small, so much as to be insignificant, and we go to 1/2, negative 1/2. Okay, so this sequence converges to negative 1/2. Another way that we can determine convergence or divergence is to use Hopital's rule. Let's look at an example. I'm going to have the sequence a sub n equals n squared over 2 to the n minus 1, and I want to show that this converges. So let's look first at the corresponding function. If f of x was equal to x squared over 2 to the x minus 1, we can apply Hopital's rule twice and say that the limit as x goes to infinity of x squared over 2 to the x minus 1 is equal to the limit as x goes to infinity. We're going to take the derivative of both parts. So in the numerator we'll have 2x, and in the denominator we'll have natural log of 2 times 2 to the x, and then we'll take the limit one more time. In the numerator we now have 2, the denominator natural log of 2 squared times 2 to the x and this limit is 0. And because f of n is equal to a sub n for n equals a positive integer, we know from theorem 9.1 that the limit of the sequence is the same as the limit of the function, which is 0. And this sequence converges. Before we go on to the next example, there are a couple of concepts I want to review, make sure that we're all on the same page. The first of these is factorial. If I have n and an exclamation point, that's read n factorial. And n factorial is equal to n times n minus 1 times n minus 2, continuing all the way to 3 times 2 times 1. The next concept I want to look at is the squeeze theorem. In chapter 1, we use the squeeze theorem to look at limits of functions and said if I have a function that is in between two other functions that have a limit, then the limit of the middle functions must be inside or between the limits of the other two functions. Here we're going to adapt that theorem to apply to sequences. So if I have the limit as n goes to infinity of a sub n, and that equals L, which is also equal to the limit as n goes to infinity of v sub n, and there is an integer n such that a sub n is less than or equal to c sub n, which is less than or equal to b sub n, for all little n greater than capital N, then the limit as n goes to infinity of c sub n must be L. Okay, we want to show that the sequence c sub n, which is equal to -1 to the n power times 1 over n factorial we want to show that that converges, and then determine where it converges. Okay, to use the squeeze theorem, I'm going to have to find two functions that are related to c sub n. Okay, one has to be more and one has to be less. Okay, so I'm going to use as my other two functions a sub n equals -1 over 2 to the n power, and b sub n equals +1 over 2 to the n power. Okay, both of these converge to 0. So if we can show that this is in between these two, we know that it also must converge to 0. And now we're going to compare the term n factorial to 2 to the n power. So let's look at n factorial. N factorial is equal to 1 times 2 times 3 times 4 times 5 times 6 all the way up to n, which if I took those first four terms, 1 times 2 times 3 times 4 is 24 times 5 times 6 up to n, where n is greater than or equal to 4. And now let's look at 2 to the n power, which is equal to 2 times 2 times 2 times 2 and so on. Again, looking at the first 4 factors, I would get 16 times 2 times 2 times 2 for n greater than or equal to 4. So for any n that's greater than or equal to 4, I can see that 2 to the n is going to be less than n factorial. Because here I only have 16, I keep multiplying by 2. Here I have 24 already, and I'm multiplying by numbers larger than 2. So the factorial is definitely going to be larger. So I can have negative 1 over 2 to the n it's got to be less than or equal to negative 1 to the n times 1 over n factorial, which must be less than or equal to 1 over 2 to the n for any n greater than or equal to 4. So it follows that the limit as n goes to infinity of our function negative 1 to the n times 1 over n factorial must be 0. In the first part of this section, we looked at finding terms when we were given the rule. But sometimes we are given the terms and we need to find the rule. So we're going to practice that. So here are some terms. And we need to find a rule that fits these terms. When we're working on a rule, we want to try to always have a sub 1 be involved in our rule. So looking at the numerators here, I see that these are all powers of 2. So it might be a good rule to have 2 to the n. And it seems to work for all of those. And in the denominators, I started with 1 and I kept adding 2. So I could say 1 plus 2 times n but this doesn't work really for this first one. 1 plus 2 times 1 would be 3. So instead of that, let's start with negative 1. Now I have negative 1 plus 2 gives me 1. Negative 1 plus 4 would give me 3. So this is my rule. Okay. Now I want to determine, does this converge? I'm going to take the limit as x goes to infinity of 2 to the x. I'm going to rewrite this as 2x minus 1. I get the limit as x goes to infinity, 2 to the x natural log of 2 divided by 2. And that is infinite. So we could say that this sequence diverges. In this sequence, the terms are negative 2 over 1, 8 over 2, negative 26 over 6, 80 over 24, and negative 242 over 120. When I look at the numerators, the first thing I notice is that they alternate between negative and positive and negative and positive. So that gives me a clue that I need to have negative 1 to the n power as part of my numerator. The other thing I notice is that these are all very close to powers of 3. They're one less than a power of 3. So the other part of my numerator is going to be 3 to the n minus 1. When I look at my denominators, I can see that these are the factorials. This is 1 factorial, 2 factorial, 3 factorial, and so on. So for the denominator, I'm going to write n factorial. Now I want to find the limit as n goes to infinity of the absolute value of a sub n and remember that the limit of the absolute value, and remember that if the limit of the absolute value is 0, then the limit of the function itself is also 0, is equal to the limit as n goes to infinity. And I'm going to eliminate this negative 1 to the n power because of that absolute value. So on the top, I'm just going to have 3 to the n minus 1. And then the denominator will be n factorial. Okay, if you think about it, n factorial is going to grow much faster than 3 to the n, because here I keep multiplying by 3. Here I multiply by a larger and larger number. So that limit is going to be 0. So we could say that this sequence that's defined here converges to 0. Okay, before we go on to the last two examples, here's a couple of definitions we need. Monotonic. If a sequence is monotonic, then either the terms are always ascending, or the terms are always descending. Okay? If we were to graph these, a function that's always ascending, of course, would look something like this. And a function that's consistently descending might be like this. A function that ascends and then later descends, or the other way around, is not monotonic. The other concept we need to think about is boundedness. For a sequence to be bounded is just what it sounds like. Okay, the sequence comes up and it approaches some limit like an asymptote. It is bounded above. If the sequence looks more like this, and is approaching some number that it will not go below, that's of course bounded below. Okay, some sequences are bounded both above and below, in which case we would just say that they are bounded. Okay, let's look at some sequences and see if they are monotonic. We've got a sub n equals 3 plus -1 to the n. Okay, and this is kind of a real giveaway when I have negative number to the n power. I know that this is going to be alternating between +1 and -1. So the terms are going to be positive, negative, and so this is not monotonic. Okay, because it just shifts back and forth between positive and negative values. So let's look at this sequence. Okay, and as this sequence goes on, here I'm multiplying by 2, here I'm adding 1. So this term is getting bigger much faster than this one is. So the whole thing is going to be larger and larger. Let's look at this mathematically. If this is b to the n, 2 to the n over 1 plus n, then b to the n plus 1 would be 2n, 2 times n plus 1 over 1 plus 1 plus n. This is b to the n plus 1. This is b to the n. Can I demonstrate that this is always larger than this? I'm going to cross multiply here. So I have 2n times n plus 2. I want to know, is that always greater than 1 plus n times 2n plus 2? Over here, I'm going to get 4n plus 2n squared. And on this side, I'll get 2n squared plus 4n plus 2. Okay, when I look at things that are common to both sides, this and this are going to be the same size. This and this are going to be the same size. So I have nothing over here, but I have a 2 left over here. So I have shown that this side is always going to be larger than this side. So this is monotonic. Okay, let's look at c sub n squared over 2 to the n minus 1. Well, let's look at the first few terms here. I'm going to have 1 squared over 2 minus 1, which is just 1. My second term would be 2 squared, so 4 over 2 squared there would be 4 minus 1, so this is 4 over 3. My third term would be 3 squared, so 9. And then this is 2 to the third is 8 minus 1, so 9 over 7. Well, I know that 4 over 3 is greater than 1, but what about here? Is 4 over 3 greater than or less than 9 over 7? If we compare the decimals here, we have 1.33, and 9 over 7 is approximately 1.28. So this is smaller than this, and so this is not monotonic. We're now going to look at whether a sequence is bounded. And this is important because if we can determine that a sequence is bounded and monotonic, then we know that it converges. So if I have this sequence, a sub n, that's equal to 1 over n, is this bounded? It is, because when n is 1, this is 1, and when n is anything bigger, this is going to get smaller and smaller and smaller, but never be negative. So the lower bound would be 0. So this is bounded and monotonic. Okay, let's look at another one. If I have b sub n equal to n squared over n plus 1. Okay, this one is monotonic because n squared is going to increase faster than n plus 1. And so it's going to be increasing. And it's bounded below, but it's not bounded above, because this is just going to keep getting bigger and bigger. So in this case, it does not converge. Okay, in our last sequence, C of n, negative 1 to the n power. Okay, this is bounded because all the values are going to be either negative 1 or positive 1, so it's not going to go outside of that. But because it keeps flip-flopping between positive and negative, this is not monotonic. And so we'd have to say that it diverges.